Okay, welcome back. This next one is definitely the format that isolates for the new aspect of this section. You're given the original function f of x, you're given its derivative, and you're given its second derivative. So it's not testing do you know how to take a derivative, it's testing if you're given the derivative, do you know what to do with it. Using the second derivative test, determine the relative extrema of the function. So, and I should erase second derivative test and put combo test. Using the combo test. So step one is critical points, or critical numbers if you want, critical numbers. Whoa. From f prime of x equals 0. And our second point is evaluate, or diagnose if you want. Diagnose is a little bit better. Diagnose critical points, critical numbers, using f double prime of x. Okay, so for the first part, we have 6x over x squared plus 3 all squared is equal to 0. I'm going to cross multiply, so 6x is equal to 0 times x squared plus 3 all squared. That means 6x is equal to 0, which means we have one solution, x is equal to 0. Now we diagnose it. F double prime at 0. So I'm just taking this number, plug it in there. Whatever I got for my critical points, I'm going to plug them into the second derivative. We only got one, so there's only one thing to plug in. So we have negative 18 times 0 minus 1 divided by 0 plus 3 cubed. So negative 18 times negative 1 divided by 27. I get a negative times a negative over a positive, so I'm going to get an overall positive. That means f of x is concave up at x equals 0. So x equals 0 is a local min. So it has this shape, and then there's a place where the derivative is 0 in the vicinity. So that means the tangent line is horizontal in the vicinity. You get something concave up there, that has to be a local min. Then we'll get the y value. Y equals f of 0. So 0 squared divided by 0 squared plus 3. 0 over 3, which is 0. So local min at 0, 0. And I'll quickly graph it. X squared divided by x squared plus 3. Looks like a big bunch of nothing unless you zoom in. Okay, I'm going to go from minus 3 to 3. And the y-axis I'll go from negative 0.5 to 2. There's the graph. So we found that there's a min at 0, and that's exactly what the graph shows. So to compare and contrast first derivative and second derivative test. So the first derivative test is the increasing, decreasing. The second derivative test is the combo test. Both tests are used to diagnose where a function has local max and local min. They both start the same way, by taking the first derivative and setting it equal to 0. The Increasing decreasing test includes solutions for f prime of x does not exist, whereas the combo test does not. You have to exclude those from the analysis. The first derivative test requires that you make a number line. The combo test does not. The combo test requires that you calculate the second derivative. The increasing decreasing test does not. That's the big distinction. There's also some x values that fail the combo test. If you get a critical number and plug it into f double prime and you get 0, 0 is neither indicating concave up or concave down from that information from the second derivative. So you'd have to fall back on the increasing decreasing test to diagnose that critical point, and that happens sometimes. All this paragraph says all that in text. Another way we can summarize all of those results is as follows. We can say that if we have a function that has a positive derivative and a positive second derivative, we can combine those two pieces of information to say that that region of the function with those properties is going to be increasing because the first derivative is positive, and concave up because the second derivative is positive. That will look like this graph, increasing and concave up. If instead the first derivative is positive but the second derivative is negative, then first derivative positive means the function is increasing, so the bank account's going up. Second derivative negative means it's decelerating, so it's going up slower and slower as time goes on. So it's concave down, increasing. It's going to look like the second graph. What if we switch it? What if the first derivative is negative, so decreasing, but it's concave up? That means the bank account's going down, but the rate at which it's decreasing is slowing. So that would be the third graph. And if they're both negative, if the function's derivative, so f prime is negative and f double prime is negative, so that means the function will be decreasing in that region and concave down in the region. It'll be this graph. And we're going to use this to actually graph functions using calculus. What it should remind you of, if you're doing it properly, it will remind you of when you were a little kid. I don't know if maybe it stopped. Maybe people stopped having these things, but connect the dots pictures. So you'd have the first dot, there was a 1, be a dot over here, there'd be a 2, dot over here, there'd be a 3, dot over here, there'd be a 4. So you just doing the little kid thing. I'm still a little kid. You just connect the dots, right? Except we're going to do this connect the dot thing by first creating the dots. We're going to create the dots by looking for max and min and looking for inflection points, and maybe throwing a few extra dots in for good measure, like just evaluating the function at some x value that we're curious about. We want to know what the y value is. Putting all those points down, and then using this information about increasing, decreasing, concave up and concave down to decide how to connect those dots, because they may not be best connected with straight lines. We may want to connect them with a curve. For example, we might want to have concave up here. Well, I have to add a little bit of curve. I have to add a different y value for that one, so it makes sense. But so I'll put a 3 there, and then we're going to do a concave down in this region, and then we'll do a concave up in this region, and then we'll do a concave down over here. So maybe it's something like that, where we're looking at increasing, decreasing, concave up, concave down, and that's telling us how we would join the different regions of the graph together, how we would connect the dots. It is kind of neat and reminiscent of a childhood activity that at least I did when I was very little. Maybe you did it too. Before ending this lesson on what the second derivative tells us about the original function, I want to show you what could exam questions look like. And what are good exam questions? So here's an example of a good exam question. You're not even given the original function. You don't need the original function to answer the following piece of analysis. You're just given f double prime. F double prime of x is x to the 4 times x to the 5 times x plus 2 all squared. And you're asked, based on that second derivative, where is this function concave up, where is this function, concave down, and where is the original function, f of x, have inflection points. So we're going to set f double prime of x equal to 0. So we get x to the 4 times x minus 5 times x plus 2 all squared equals 0. And we're going to have three different solutions. We have the first part being 0. So x to the power 4 being 0 means x is 0. We have the second part being 0. X minus 5 being 0 means x is equal to 5. And we have the third part, x plus 2 being 0 means x is negative 2. So I'm going to make a number line. Number line is going from minus infinity to infinity. I'm going to cut the number line up at those x coordinates from the smallest to the largest, negative 2, 0, 5. They have to go in the right order. Now I'm going to choose test values. How many do we need? We need one for each region. So I'll pick minus 4 for the first region, minus 1 for the second region, 3 for the third region, and 7 for the last region. Those are just numbers chosen to represent that entire region of the number line. Now we're going to plug those test values into the second derivative. So f double prime at negative 4. We're going to have negative 4 to the power of positive 4 times negative 4 minus 5 times negative 4 plus 2 all squared. So that'll be a positive number times a negative number times a positive number. So negative 4 to the power of 4 is negative 4 multiplied by itself 4 times. It's an even number of times. A negative multiplied by itself an even number of times is going to give you a positive. Negative 4 minus 5, that's negative 9, that's a negative number. And then the last one, negative 4 plus 2, well, that's negative. So negative 2, but it's negative 2 squared. So negative times negative, positive. Overall, we get a negative, and that means it's concave down. From negative infinity to negative 2. And I'll change the color of that so it's easier to figure out what came from where. Concave down from negative infinity to negative 2. I'll put the little down shape. And I'm going to do the next test value, f double prime at negative 1. So negative 1 to the power of 4 times negative 1 minus 5 times negative 1 plus 2 all squared. So we're going to get positive again, times negative again, times positive again. We're going to end up with a negative. So it is again concave down in the next region. From negative 2 to 0. Now we're going to check the next test value, f double prime at 3. So 3 to the power of 4. Notice no matter what you plug in that first piece, it's going to be positive. Power of 4, plug something negative or positive in, you get a positive number. Okay, then we have 3 minus 5 and 3 plus 2 squared. You get positive, negative, positive. We get a negative again. So it's still concave down. So it's concave down from 0 to 5. And now there's one more test value. We're going to plug 7 in. F double prime of 7. 7 to the power of 4. Please don't calculate this. It's a big number. 7 minus 5 times 7 plus 2 squared. Finally, it changes. It's all positive. So we end up with concave up on the last region. From 5 to infinity. Okay, where do we have an inflection point? There's only one, where it changes its concavity, and that's happening at x is equal to 5. So POI at x equals 5 only. The only spot where the concavity changed. Next example, next test or exam style example. We're told a pile of information. F double prime of x is equal to 0 at the following x values. -5, 0, 5, 22, and 50. And we're told that the second derivative at -5 is 2. Second derivative at 0 is -4. Second derivative at 5 is 8. F double prime of 22 is equal to 0. F double prime of 50 is equal to -16. Determine the x-coordinates of any local extrema. We have to use the combo test. We are forced to use the combo test. So x equals -5, x equals 0, x equals 5, x equals 22, x equals equal to 50 are critical numbers. F double prime at -5 equals 2 is positive. That means concave up at x equals -5, and that means local min at x equals -5. Okay, now we'll do the next one. F double prime at 0 is equal to -4, which is negative. That means it's concave down at x is equal to 0. So that's a local max. So I'm just going to highlight the answers here. Local min at x is equal to -5. Local max at x is equal to 0. And we'll go to the next one. +5. F double prime of +5 is 8, which is a positive number. That means it's concave up at x equals +5, and that's going to mean a local min. Okay, so that's our next conclusion that we can draw based on this data. F double prime at 22 equals 0 is inconclusive. It's not plus or minus. Inconclusive at x equals 22. And there's one more. F double prime at 50 is -16, which is negative. That means concave down at x equals 50. So that means there's a local max at x equals 50. So there you have it. For 1 point, we couldn't say anything. Second derivative being 0 does not tell us any information. It means the combo test fails. And we would need information about the sign of the first derivative to the left and to the right of 22 to see if it's increasing and decreasing on either side in order to diagnose if it's a max or a min. Okay, another one. All data, no function. We're told that the second derivative is 0 at -5, 0, 5, 22, and 50. Aha, same x values, but different information otherwise. We're told that the second derivative is negative in some intervals and positive in other intervals. Determine the x-coordinates of any points of inflection. So what I'm going to do is I'm going to create the number line, create and fill in info on number line. So it's a lot of info, so I need a big number line. I'll do the whole page. I suggest you do the same in your notes for copying this, which you should be. Okay, so we're -5, 0, 5, 22, 50. Next, I'm going to plug in whether the second derivative is negative or positive in each of those subdomains. So the first one, from -infinity to -5, it is negative. So f double prime negative, that means concave down. It's also negative from -5 to 0. So f double prime negative, so concave down. It's also negative from 5 to 22. F double prime negative, so concave down. And from 50 to infinity, f double prime negative, concave down. Then I'm going to label in the concave up information. Second derivative is positive from 0 to 5, so f double prime of x positive, concave up, and from 22 to 50, concave up. Now we have to look for inflection points. Wherever it changes concavity, there's going to be an inflection point. So we can say there's a POI at x equals 0, but not at x equals -5. At -5, it's same concavity on both sides. There's another inflection point at 5. There's another inflection point at 22. And there's another one at 50. And this type of question might ask, how many inflection points are there? So the answer is 4. There's one special x value that did not have a critical point because its concavity was the same on both sides. The last exam style question is kind of a nightmare question. We have information about the first derivative and information about the second derivative. We're asked for finding x coordinates of inflection points and x coordinates of local extra. That should be extrema. That's a typo. Local extra. Local extrema. All right, so I'm going to make two different number lines. I'm going to say the first one's the f prime of x number line, and the second one is the f double prime of x number line. So I'm going to put down those special numbers that are in the question. The first derivative is 0 at 4, 10, and 25. And then we have information about the first derivative being negative for -infinity to 4. So f prime negative. That's decreasing in that region. And we have it's also negative from 4 to 10. So it's decreasing in that region. And 25 to infinity. So it's decreasing in this region. And we have increasing regions. or just one of them, from 10 to 25. F prime of x positive. Now, based on this picture, we can tell that there is a min a local min at x equals 10, and we can tell that there's a local max at x equals 25. Now for our second derivative number line, go from minus infinity to infinity, we cut it at -4, +4, +15. Now I'm going to label the pieces. We have a first region from -infinity to -4, which is a negative second derivative, so f double prime negative, so concave down. And the same thing's happening from 4 to 15. And we have f double prime positive, and the other two regions from -4 to 4. And from 15 to infinity. So we can tell that there's points of inflection at several locations. There's a POI at -4, at +4, and at 15. Okay, and that's it. See you next time.